So now let's continue with the etching process. So for the etching process, we care about first is the etching profile. So this can be isotropic or anisotropic, or can be a mix of the profile. For example, if we look at here, this one is anisotropic profile. This is the tapered or sloped profile, and this is the both profile because of the lateral etching. Next one is the selectivity. So it's the selectivity between the film material and the resist, or the film material and the mask. The third one is the uniformity, including across the wafer, uniformity across the wafer, or the thickness variations with the feature size. So this is the macro loading effect or macro loading effect, or ARDE. This is the aspect ratio dependent etching effect. The last is the surface quality. It is the contamination or damage on the surface. So now first we look at the macro loading effect and ARDE effect. So macro loading and the aspect ratio dependent etching. For the macro loading, it refers to the effect that the etching rate depends on the local pattern density. As you can imagine, so we have more open area. So more open area to etch. More open area to etch. It will etch slower. So normally this will etch slower because the reaction will be depleted by the larger open area. Some exception is like, for example, if we etch acetic oxide using this gas, but this one the etching will be very uniform. There will be no loading effect because this one we need ion bombardment. So as long as we have uniform ion bombardment, we get pretty uniform etching. But normally when we etch silicon, for instance, if we use SF6 to etch silicon, but this is pretty chemical etch. So when we have the chemical etch, so we have this macro loading effect. That means we have bigger open areas to etch, the etching rate will become slower. The second one is the aspect ratio dependent etching process. It's also called RE lag. That means the smaller features etch slowly, as you can see here. So bigger features etch to the bottom, smaller features etch slower than the bigger features. So this is because for the smaller features, the etchant, including ions, are more difficult to pass through the smaller holes. Secondly, the etch product is also harder to diffuse out. For this one, hard to get in and also hard to get out. This includes the ion bombardment. The lower pressure can minimize this aspect ratio dependent etching effect because we have more directional ion bombardment and a longer mean free path. So it's easier for the etchant to reach the bottom and for the etch product to come out. But this is another example of this aspect ratio dependent etching. You can see, so here open area etched deeper than the narrow trenches. So now let's look at when to stop the etching. So normally the etching is divided into the main etch and over etch. For example, here we use the photoresist as the mask to etch this film. First, so we have the main etch. Then after the other material is almost gone, so we have the over etch. We need the over etch to make sure that all the material they are etched away. But this is the before the over etch. This is after over etch. As you can see, some of the substrate material may be etched. But this depends on the selectivity between the etched film and the substrate. Obviously, the higher the selectivity, the better. There will be less etching into the substrate. And now the question is, so when can we know the etching reached to the substrate? This can be done by the optical endpoint detection. So optical endpoint detection, so we can tell when the substrate gets exposed. So now we will look at the optical endpoint detection. So we know that so each atom or each molecule, they have their own emission wavelengths. So the color of the polymer changes when etch different materials. So the color comes from the excitation of the electrons. For example, the molecule can go to the higher state, then excite to this, then go to this lower state. It may emit the light here. Then it can go to the ground state. It may emit a light again. So this can happen. This can also happen. So different materials, different molecules, the light wavelength will be different. So the wavelength is given by 1240 divided by E. So this is the nanometer. So 1240 nanometer divided by E. E is electron volt. For example, when we have 3 electron volts, then this will be about 410 nanometer. So we use the optical sensor to tell when the etching is done. For example, when we etch silicon using the fluorine and oxygen gas, the species can be silicon fluoride. The wavelength is 440 nanometer or 777 nanometer, and this is the different colors for the different materials with different etching gases. Here is the schematic of one example. As you can see here, so here is the signal intensity. This is the optical signal intensity, light intensity. So here first we have this gas. So this is the etchant gas. Then we turn on the ion power so the etch start. So when the etch start, we get this red color curve. Red color is correspond to the etched product. Then the etchant will be consumed, get lower signal. At this point here, so the red color drop first, and the green color show up. This green color is the etching of the substrate product. So then we know, at this point we know that the substrate material is exposed to the etching. Then we can do some, maybe we can stop here, we do some over etch, we stop here, then it will be good. So now let's look at the etching of the different films. So normally the etchant gas contains halogens. For example, fluorine, chlorine, bromine, iodine. So normally fluorine is very popular, chlorine is also popular, bromine is less popular, iodine I haven't seen one. Other gases like oxygen. So oxygen will etch the polymer. So polymer material of carbon or diamond, with carbon, can be etched with oxygen. Other material like CH4 is also used sometimes, and some argon for the physical bombardment, nitrogen sometimes, and maybe helium for the dilution. Hydrogen for the etching, or for some hydrogen for the etching, and also for the dilution. So how to choose what gas to use? This depends on the ability to form the volatile byproducts. And secondly is the selectivity and the anisotropy. For example, if we want to etch aluminum, so we cannot use this gas, fluorine gas will not work with aluminum because this one is very high boiling temperature. So when we have very high boiling temperature, that means it's not volatile. For chlorine gas, Cl2, so this one 178 degrees, this one is okay. So we use chlorine gas to etch with aluminum. It's also possible to use the bromine gas, but normally we use chlorine gas to etch with the aluminum. For other materials like carbon, so carbon can be etched away by the fluorine gas and the chlorine gas, and also hydrogen. This one I'm not clear. It looks like it's okay, but I don't think people etch carbon with hydrogen gases. For copper, you see this one very high boiling temperature is hard. This chlorine gas is also very high boiling temperature. It's also difficult. For bromine gas, it is the same thing. So for the copper, we cannot etch chemically. So the chemical etching of copper will be difficult. What we can do, we do the spacer. So we do the ion bombardment. We rely on the ion bombardment to etch away the copper. So those materials, titanium, tantalum, and tungsten, so they can be etched away by the fluorine gas and chlorine gas. For some other material like indium, so indium can be etched away by the chlorine gas, and also it can be etched away by in the form of this one. This is this gas, methane gas. So methane gas can be used to etch away the indium. For example, if we etch ITO is the indium tin oxide. So this is the most popular, they call the TCO, transparent conducting oxide. It's transparent. So this material ITO is transparent, and it is also conducting. This is very useful for the LCD display. It's very popular for the display because this one, for the display, we need it to be transparent and also conducting. So it's very popular. This one can be etched away by the mixture of those two gases. So the hydrogen can take away the oxygen. The methane can etch away the indium to form this one. And now I want to ask you, how to etch away like gallium arsenide. So this is as we know, this is the most popular group 3,5 semiconductor materials. So how to etch away gallium arsenide? So we can use a chlorine gas. You can see for the case of gallium here, fluorine, very high boiling temperature. The boiling temperature is too high, so this is not good. Sorry, fluorine not good, but chlorine, 200 degrees, so this is okay. It is volatile. But 200 degrees is the boiling temperature. So even below the boiling temperature, it is volatile in a vacuum, pretty much vacuum during etching. So the gallium we etch with the chlorine is okay. So arsenide is here. This one, you see the chloride is 130 degrees, so it's also okay. So that means another material like indium phosphide. So indium phosphide can be etched away by the methane gas, and it can also be etched away by the chlorine gas. The same for the ITO. ITO can also be etched away by the chlorine gas. The etching rate is faster. But this gas is more, maybe higher selectivity, more gentle. So this is the list of different materials to be etched by different gases. So this, because here we have this textbook is the silicon VRSI. So it only talks about silicon and silicon nitride, aluminum, those materials used for the IC manufacturing. So this one is from another textbook for what material to be etched by what kind of gases. For example, you can see here, for indium phosphide, we use methane and hydrogen gas. So now first let's look at the etching of the silicon dioxide. So normally we can use CF4 to etch away the silicon oxide, but this is nowadays people use more and more this gas. They use C4F8 and oxygen. This also etch away the silicon oxide, which is a very good property. Another choice is this is also popular, CHF3 and oxygen. So those CF4, this one also has some oxygen sometimes, but they are popular agents for the oxide etching. So if we use CF4, it generates CF3 plus fluorine. The fluorine reacts with the silicon oxide to form the silicon tetrafluoride, but that is volatile. So the etching is mostly done by the reactive neutral species. In this case, it is F, it is the fluorine atom. If we add some oxygen, so oxygen will combine with CF3 to form COF2 or maybe COF3, for those things. That means the CF3 can be activated, but can be removed by the oxygen. So when the CF3 is removed by the oxygen, it will go more to the red side. So you generate more fluorine. That means when we add oxygen, we get more fluorine because agent. This reaction goes to the red side when this one is activated by the oxygen. So we have the higher fluorine concentration, and this gives you a slightly higher etch rate. But when you have too much oxygen, it will reduce the etch rate because of the dilution. So the oxygen will dilute the fluorine gas, and competition of oxygen with fluorine for the surface side. If the surface silicon you have lots of oxygen, then the fluorine it blocks the fluorine coming to the surface. So this also slows down the etching. And the reversal of the second reaction. So this one, if you have too much oxygen, it goes to the left side, so the etching will be slow. So the process can be chemical. That means the fluorine will etch away. This reaction is chemical reaction. No need can etch without ion bombardment. So we do not need ion bombardment to etch. So that's why I said a chemical. So when we have chemical, it is the isotropic and it is selective. But when we have low pressure, well below 100 milliliter, so the ion energy will be high. Then we have this damage-driven ion-enhanced etching process. That means when we have the ion energy is high, the bombardment to the silicon oxide, it will form dangling bonds. It forms the dangling bond. So those dangling bonds, chemical bond, the dangling chemical bond make the material etch easier. So that means if we have the structure like this is the mask. So the bottom part, we have this bombardment. So the bottom part will etch faster than the lateral etching. then we have this isotropic etching. So the situation is similar to the SF6 and NF3. That means when we have this high ion energy, so ion damage to make the doubling bond, we have the etching. Then the etching will be more vertical etching. So to promote isotropy as well as increasing the selectivity to the silicon, so we should reduce F and increase carbon. So because the etching by F is the spontaneous, it is spontaneous. Then the reaction will take over right away. But etching by the CF3 or CF2, the etching by the CF3 or CF2, this is the ion enhanced. So that means the etching will be very, very slow without ion enhancement. But with the ion bombardment, the etching will become high. Then we get more anisotropic. This when we have this one, when we increase the, so when we have this one CF2 from the fluorocarbon polymer is increased, then we get the side wall, protect the side wall. So this will also increase the anisotropy. So to reduce carbon, to reduce F, so we can add some hydrogen. So hydrogen will react with F to form HF. Or we can use the fluorine poor and the carbon-rich gases. Like this one we have hydrogen inside. This one smaller carbon. This is also smaller fluorine poor. So this is the smaller amount of the fluorine. You can see this one C2H6 carbon and F equal to 2/6. CF4. So carbon over F is 1/4. So the ratio is different. This one has more fluorine. When we have more fluorine, it's more isotropic. So now let's look at the effect of adding the hydrogen. So when we add hydrogen to the plasma, when we add hydrogen to CF4 plasma, it will form HF. This is not very reactive. So the F will be consumed. F will be consumed by the hydrogen to form HF. Then the F over carbon ratio will be smaller. This slows down the formation of silicon tetrafluoride and the reduction of etching rate. So with less fluorine, so the chances of the CF2 or CF3 to compare with the fluorine to form CF4 is lower. So there will be higher concentration of CF2 or CF3. But this is promoted of the fluorocarbon polymer. We know that for the fluorocarbon polymer, this is the fluorocarbon polymer. So fluorine over carbon equal to 2/1. If we have this one, CF2, this is the ratio is also 2/1. The CF3 is 3/1. It's close. For those polymers, this will promote the formation of this fluorocarbon polymer. So the adding hydrogen increase selectivity of the etching of silicon oxide, and which reacts to the silicon. But that means the silicon oxide etching rate will be constant, not too much. It will be reduced, but not too much. But silicon etching rate will be much more reduced. But this is because for the silicon oxide, we have this here. We have this oxygen. So it contains oxygen. So this can remove hydrogen and the carbon to form water and CO to maintain the fluorocarbon ratio. So basically, you can think the oxygen can burn away the carbon and burn away the hydrogen to have more fluorine, because this one we have oxygen from the silicon oxide. For the silicon, there is no oxygen here, then this will not happen. So the silicon will be actually slower because of the reduced fluorine to carbon ratio. If we have too much hydrogen, there will be no etching because you have too much polymer formation. So another explanation is like this. So when we have this one, CF3 to come to the silicon oxide surface, so we have it comes here like this, fluorine and carbon. So this carbon on the surface will react with the oxygen from the substrate to form the CO. This way, the carbon is gone, then the fluorine can come in. Here's the summary of the ratio of the carbon to fluorine. So you can see, so when we have the, so So when we have less carbon, when the ratio is low, so when the ratio is low, we have too much fluorine. When we have too much fluorine, we have this lateral etching. So we have this lateral, but we have still more vertical etching because iron bombardment, more vertical etching, but we have some lateral etching. So when the ratio is high, we get this vertical etching. We have the sidewall passivation, inhibitor deposition on the sidewall. You can see here. So we found the fluorocarbon on the sidewall. So when we have too much carbon to fluorine, we get this tapered profile. So this is for the etching of the silicon oxide. For silicon, the etching may be stopped. As you can see here. Here is the fluorine to carbon ratio. So higher fluorine etching, lower fluorine, we have the net film deposition. This is like a PECVD, platinum enhanced chemical vapor deposition. We have the polymer formation. We deposit a film rather than to the etching. So to have higher fluorocarbon ratio, when we add oxygen, we get higher ratio because the oxygen take away CF3 to take away CF3 to produce fluorine. So when we add hydrogen, we reduce the fluorine carbon ratio because hydrogen take away F to form HF. And this will promote the formation of CF3 or maybe CF2. Now here's the iron bombardment energy. You can see higher energy promotes the etching. So this makes sense. Here you can see this graph. For the chemical silicon oxide, when we have more hydrogen here, that means we move to the left side. So the etching rate of silicon oxide gets slower, but not too much, because the hydrogen will burn away because the oxygen in the silicon oxide will burn away the hydrogen. But for the silicon, the etching rate gets much lower. And here we get a very high selectivity between silicon oxide and silicon. So silicon etching is very slow, but oxide etching is still okay. So the resist is the same thing. When we have too much hydrogen, the resist etching will also get very slow. So now let's look at the etching of the silicon. The silicon can be etched away by the fluorine and chlorine and the bromine. So in reality, this is popularly used. This is also very often. But this one is also used for the production, but not too much for research. For the fluorine, here I listed the three gases: Cl4, SF6, and NF3. But nowadays, this gas is very popular. This gas is popular maybe in 20 years ago. This gas is the more friendly to the environment, less green gas effect. So this is very popular. So when isotropy is not important, we can use SF6. This one gives very high etching rate and also very high selectivity. But this is the chemical etching. But because this one it produces more fluorine. We have 6F. F is 6. We produce more fluorine, and there is no carbon. So we know that if the carbon comes to the surface, it will stop the fluorine from coming to the surface. So carbon is not good. So this gives you the fastest etching rate, much faster than using Cl4 gases. So when we want isotropy, so we need to add some hydrogen, or we use CHF3. But when we have this one, there still may be some undercut. There can still be some undercut, depending on how much you add it. Another choice, we can use C4F8, SF6. So actually, this one is right now is very popular because this gas I think is really good. So in this University of Waterloo, so we use this recipe a lot. C4F8 over SF6. This etches the silicon very well. And this one gives you isotropy. Isotropy because C4F8 give you the polymerization on the sidewall. So C4F8, this one gives you fluorocarbon polymer on the sidewall. Or we can use the low pressure to promote ion diamond enhanced etching. This also gives you more anisotropy. But normally it's hard to achieve using the fluorine gas high anisotropy and selectivity at the same time. For example, if you use this gas, if you need anisotropy, you need to add hydrogen. But when you need hydrogen, you get low selectivity. For this one, it is okay. The selectivity can be 7/1. That means this gas can etch silicon about 7 times faster than silicon oxide, and still we get very anisotropic etching. So this is the fluorine gas. So for the chlorine gas, we include chlorine gas, HCl, silicon tetrachloride, BCl3, another one is the CCl4. This is also popular gas. So in this university, so we have this one, and we also have this one. This one is available by demand. So this gives you anisotropic etching, anisotropic and selective etching at the same time. So this one, the etch need ion bombardment. We need a bombardment to promote the etching, otherwise the etching will be slow. So because we need ion bombardment, so we get anisotropic etching without polymer inhibitor formation. So the etching of oxide, is very slow. So we get very high selectivity. So the etching rate of silicon can be 100 times the etching rate of the silicon oxide. So if we add some oxygen, we get more anisotropy because it will form a silicon oxide on the side wall. So the silicon oxide on the bottom will be bombarded away. For the bromine, it's even more like this. It's more anisotropic and selective to oxide than the fluorine and the chlorine. And adding oxygen can give you the inhibitor formation, and this gives you more anisotropic. But the etching rate will be slower. So the etching rate fastest for the fluorine, then chlorine, then bromine. Among the fluorine, this will etch the silicon the fastest. So now let's look better the chlorine gas etch over the silicon. So the undoped silicon etch very slowly in the chlorine atom or chlorine gas without addition of ion bombardment. But when we have heavily doped silicon, the etch is much faster. So the doping, that means so the chlorine etching involves electron transfer. So we have the chlorine so first, so why undoped silicon etch very slowly? So this is because of something called a steric hindrance. Because of the steric hindrance. So we have the chlorine here. But when the surface is covered by the chlorine, for the other chlorine, it's difficult to come to here to etch with the silicon. So we know that to etch the silicon, so we need 4 chlorides to form a silicon chloride. So we have this configuration. The chlorine is difficult to come below. But when we have the n-type heavily doped, so we have lots of electrons. So those electrons can be transferred to the chlorine to form this chlorine ions, to have this chlorine ion. So we have this chemical bond. So when we have this chemical bond, so somehow so the chlorine will be easier to come to the below and to go through the chlorine ion and come below the silicon surface to form the silicon tetrachloride for the etching. So this is why we need heavily doped. We need heavily doping, or we need ion bombardment to have the good etching rate. So when we have ion bombardment, so the chlorine penetration to below the top surface, chlorine penetration is increased by the ion bombardment. So this gives you the energy-driven anisotropy. So in this case, so we have the charge transfer produced isotropic etch in heavily doped layers. Because of this effect, the etch there can be a lateral etching. So we have the isotropic etching because of the heavily doped charge transfer process. So in order to have the isotropic etching, so we need side wall polymerization. This can be realized by adding some other components. For example, we add BCl3, CCl4, silicon tetrachloride. So this is actually not necessarily polymer. So based on what I read, for example, so we have this gas here, BCl3. And we found BClX on side wall. And we found the BClX on the side wall. Now if this thing comes to the side wall, it is not like a polymer. But this prevent chlorine come to the side wall. So when the side wall is covered by BClX, it's hard for the chlorine to come to the surface. And this is how the passivation, how the side wall protection works. But this is not. So obviously, this one is not like a polymer. So now let's look at the etching of aluminum. So aluminum, we know that fluorine will not work because aluminum fluoride is not volatile. So we use chlorine gas. So when we have chlorine gas, so we form this as aluminum chloride. This is a volatile at room temperature. So in this university, so normally we use this gas. Nowadays, people normally use chlorine and BCl3 to etch away the aluminum. So one issue for the etching of aluminum is the presence of the native oxide like aluminum oxide on the surface. So we know that aluminum oxide, this is the sapphire. It's very chemically stable. So it is very difficult to etch. Very difficult to etch away the aluminum oxide. So then we need a breakthrough etch before the main etch of the aluminum. So we can use argon sputter or use BCl3 or those gases to bombard to etch away the aluminum oxide by the physical and the chemical means. So the layer here may be 1 or 2 nanometer. But the etching rate of aluminum oxide can be 100 times slower than the etching rate of aluminum. So that even this 1 or 2 nanometer oxide need to this will slow down the etching of aluminum very much if they are not removed at the very beginning. But this removal we need a physical bombardment. So why BCl3 can etch away the aluminum oxide? So because first, so we have the physical bombardment. Secondly, so here we have the boron, so we form this one, BOCl. So this one take away the oxygen. So the oxygen here can be taken away by BCl3 to form this one. But for the chlorine gas, if we use pure chlorine gas, the oxygen in the aluminum oxide cannot be taken away. So once the oxide is gone, so the etching of pure aluminum, it can be etched easily by the chlorine gas, and this etch is isotopic. It's pure chemical etch. No need of ion bombardment for the etching. If we want isotopic etching, so we need side wall protection. So we need to add those gases for the side wall protection. For example, for this one, as we said, it may form BClX on the side wall. So for the IC, normally we add 1 or 2% of copper into the aluminum because the copper will reduce. It's called electron migration. If this is the aluminum, when we apply electrical field, in the aluminum atom, it can move around. This is called electron migration. By adding some copper into the aluminum, if we have some copper inside, it will not move around. So this is the purpose. But copper we know is very difficult to etch, so we need ion bombardment, or maybe very high temperature. So another problem with the aluminum etching, if we want to be precise etching, is the corrosion of the aluminum layers. So when exposed to the ambient, so because the chlorine dissolved chlorine chlorine or aluminum trichloride on the side wall, it will react with the water to form HCl. This one will etch aluminum. But to solve this problem, so first we can heat the wafer to high temperature to drive off the chlorine, or we can bury the chlorine with the CF3 polymer-induced fluorocarbon polymer. Then we can remove the polymer later. Or maybe we get exposed to the fluorine ambient, such as CF4 polymer, to replace the chlorine with the fluorine. Then we add oxygen polymer to remove the photoresist, and then we do the water risk. Then it will be good. So now let's look at the deep silica etching. Deep silica etching. This is called DRE. So this is very useful. It's very useful technique. So why we need a deep silica etching? So one problem with the plasma etching can produce deeper trenches than wet etching, but sometimes with tapered angles like this. If you have the tapered angles, you can imagine you cannot etch too deep. It is not desirable in many applications. For the deep RE process, we can have produce deep and high aspect ratio structures with vertical side wall. You can see the perfectly vertical side wall like this, very vertical side wall. So this is the most important breakthrough in the dry etching history in the recent years. So this one became popular after 1995. So this popular as the patent I think the patent. So the patent came out in 1993 and became popular in 1995. So this is the deep static etching. So the process employs alternating steps of etching and deposition. So we have a switch process. So we have in the deposition step. This deposition step gives the thin film protecting coating on the sidewalls for the vertical sidewall profile. So we use high density plasma to have high etching rate and high selectivity. So now we will look at how this works. So we use high density plasma to alternatively etch silicon and deposit etching resistant polymer on the sidewalls, as you can see here. First, we have this SF6 gas. So we know that this one it has 6 fluorine. So produce a lot of fluorine and no carbon. This gives you a very, very high etching rate. So we use SF6 for high etching rate. But the problem, this one is isotropic. It is isotropic. So then we do the passivation step. For the passivation step, so we have the C4F8. So SF6 a few seconds, C4F8 a few seconds. This one, so we know that the fluorocarbon, as we have seen before. Fluorine. So this one, the carbon to fluorine is 1 to 2. So C4F8. So carbon to fluorine is also 1 to 2. So that means this one is the most efficient to produce the fluorocarbon polymer on the sidewall. Then we have etch again. So then we use SF6. So the bottom polymer, the bottom fluorocarbon polymer, at the bottom will be bombarded away. Then we have the etching. The etching will be isotropic. The etching will be like this. In the end, we get this kind of profile. And then we etch, then we passivation, so we etch, passivate. So this is how it works. So the etching rate can be several micrometers per minute, but this is pretty fast. But nowadays, we can get 50 micrometers per minute, so this is super fast. For normal dry etching, we get only a few 100 nanometers per minute, but this one we can get 50 micrometers per minute. So we can etch away many 100 micrometers with vertical sidewalls very easily. So you can see this is a very, very powerful etching technique. We can etch through a thick silicon wafer. So the sidewall is rough because of this zigzag. The sidewall, this depends on the cycle times. So longer cycle like this, more zigzag and more scallop. So the recipe depends on the geometry. It's very popular for the MEMS, micro electromechanical system. That's common for the nanofabrication because of the zigzag profile. So now let's look at what is used for the MEMS. The MEMS, we know micro electromechanical systems. So for the cell phone, so we have this. When you turn the cell phone, the screen will rotation. So we have this called inertia device. So each cell phone have maybe quite a few inertia devices. So the inertia device is based on the silicon, and this is the most popular MEMS application. And this one we use the deep static etch. So we use So we use a deep static etch to make the inertia device. This one has controlled when you flip the cell phone, the screen will rotation. For the car, so we have the accelerator meter. For the car, we have this accelerator meter. That means when there is an accident, this accelerator meter will be triggered. Then it is the airbag. Airbag will blow up. So this is the accelerator meter is also used a lot of deep static etching. For the auto driving, the MEMS mirrors. For the auto drive, automatic driving. This also we use deep static etching. So this is very popular. So this process is called a Bosch process because the company, the MEMS company is Bosch. This is a very big German company. But actually, the Bosch have this maybe I think 1993. But in the 1980s, In 1980s, the Japanese people first proposed those switching, the switch between etch and passivation step. So this idea is proposed by the Japanese, but the Bosch process used SF6 and C4F8 gas. So those are much popular, most efficient gases. So even today, we still use the Bosch process. So here's one example of the Bosch process. You can see, for the passivation, we use C4F8. For the etching, for the etching step, we have the SF6. For the passivation, we do not need any power, pure chemical deposition. For the etching, we need some bombardment, so we use 12 volt. Coil power, this is ICP power. ICP coil power is 600 watt. Time is 7 seconds, 9 seconds. But nowadays, the time can be less than 1 second. So the machine is become much more faster than before. We can have the switching time, the cycle time be less than 1 second. So we have shorter time. This side valve zigzag will become, the zigzag. This zigzag will become smaller. So from here to here, you can see from here to here is 1 cycle. From 1 cycle. So here's the example of the deep silicon etching. So we use low ion energies. Low ion energy. So this 12 watts is not very high. Low ion energies. This gives you less damage and higher selectivity. It can reach 100 to 1 for the resist. This is very it's so good. 200 to 1 for the silicon oxide mask. A very high selectivity. But this process here cannot give you this high selectivity. To give you this very high selectivity, you need a 3 step. We need 3 steps. That means that is the etch. So we have the deposition. So first we use this one. Then we use H1. It's something like this. This you can see H1. Then we use H2. We have the H2. In the H2 process, it's very similar to this one, but know that the polymer, the fluorocarbon polymer is already removed. During this step. So the H2 we have 0 watt. So this part becomes 0 watt. The pure chemical etching, this gives you much higher sensitivity. So the H1 is called the breakthrough to remove C4F8. So this step only remove C4F8, remove the fluorocarbon polymer. Then we have this H2, pure chemical etch to etch away the silicon. It is very powerful. So in short, this deep RE, so very high, extremely high etch rate, so very good selectivity, and it's very anisotropic. It gives you the vertical side wall. So you can see high rate, high selectivity, and very anisotropic. The main problem is we have the side wall is not so smooth. So here, like example, you can see the side wall. This is the zigzag side wall. This is the micro gripper. You can something here can be grabbed by this micro, like a tweezer. But those are structure made by the deep silicon etching. They are all deep silicon etching. This one you can make something like this or something very high aspect ratio structures. But nowadays you can etch easily like 600 micrometer silicon can be etched within a few hours. So one issue for the deep RE is the etch rate varies. This is as we have seen before, it's called aspect ratio dependent etching, ARD effect. So you can see, so narrow trench etch shallower than wider trenches. So narrow trench is difficult to etch. You can see here. So we have the trench width. We have narrow trench, so the etching rate drop a lot. So this is because the etchant, and the ions, and the etchant, fluorine, is more difficult to come to the bottom. So how to solve this problem? To etch ultra high aspect ratio hole or trenches, so we can, for example, ramp up gradually the baggage power along the etching. That means maybe we etch here, we use maybe 10 watt. We etch here, use 15 watt. Or we etch here, use 20 watt. This RF, this one. So you change this power along the etching. So deeper etch, you need more power, so that you have the more ion bombardment come to here, bombard to the bottom. So this is the deep static etching. The last example is the laser-assisted chemical etching. In this case, we use the laser to create chlorine radicals to etch the silicon. So we know that chlorine etch silicon easily, but this one, no etch with the silicon, or almost no etch with the silicon. So we use the laser beam. To create chlorine after this Cl2. So this will react with silicon to form the silicon tetrachloride. You can scan the laser beam along the surface. Then you can have this 3D structure like this. But this one I think is not so popular. I have never seen one. Thank you.